Bismillahirrahmanirrahim. So in this video for this week we will be talking about unsupervised learning. In our previous videos last week we looked at the supervised learning. So the decision tree, the naive Bayesian classifier, they were both examples of supervised learning. Now the difference between an unsupervised and a supervised learning is that in the case of the supervised learning, the training data, that's the observations and measurements, are also accompanied by a label. So the label is important, and the label indicates the class of the observation, and this forms the training data, and any new data that comes is then classified based on the training data. So we know all the labels, and the new data is just classified into one of the existing labels. In the case of unsupervised learning, which is also known as clustering, the class label of the data is missing, so this is unknown. So if we have a set of measurement or observations, what we do is we look at this with the aim of establishing the existing class or clusters in the data. So we don't have a training data to look at, but we take the data itself to form groups or find any patterns that are inside that data. So the rest of this lecture is going to be on the unsupervised learning. So suppose we have a set of data. Mostly in machine learning, the data is usually represented as a form of a matrix. So in this data model, there is a set of features f1 through fn, which are also sometimes called attributes, and a set of instances, also called samples, x1 through m, and each instance is actually a subset of the feature set. So every instance or every sample is an occurrence of these set of features. So typically, as I said, it's made up of a matrix or a tabular form. So we may have something like this. We make a table here. So we have all our features f1 and then f2 and so on, and the last feature is here f of n. So these are all the features, and then for the data itself we are capturing data for every sample or every instance, and the data is given by x1, x2 and so on up to x of m. So a value over here means the occurrence of this feature in this sample, and usually it can be a 0 or a 1, which means if I put a 0, it means that these features occur in this sample, and if I put a does not occur in this sample, and if I put a 1, it means that f2 occurs in x2. But it doesn't have to be 0 or 1. I can use the frequency, so I can write something like 3 over here, or I can even have 0.5 or 7.69, depending on where the data is coming from. Usually for scientific equipment such as medical equipments, acoustic equipment, sensors, you end up with the real values, and for dyadic data you have something like 0, 1, and in some cases you have the frequency of occurrence, how many times this feature occurs in this instance. So this is how the data is usually represented, and you can see that if I want to look at x1, it's a combination of the occurrence of these features f1 through fn. So x1 basically is this data, and if I want it, I can also write it at x1. So this is also a vector. If I take the entirety, it's also a vector. So x2 similarly can be x2. This is also a vector. So I can look at it in the form of a matrix. Though this is a matrix, and I can look at the individual x1, x2s are the rows in the form of vectors as well. And I'll be using these two notations in this video. So let's look at this example. This is the similar example to what we had in the case of the decision tree. So we had whether it's sunny or rainy, and the temperature is warm or cold, what's the humidity, and then we were trying to predict whether play tennis is a yes or no. So in this case we have 3 yeses and 1 no. What we can deduce from here is, so this is the classes, we have 2 classes, yes and no. For yes we have this as set of features, and for no we have this set of features. So this is the case of the supervised. In the case of the unsupervised, this is missing, this part is missing. So the data is there but we don't know the labels. So we are trying to find out these labels. Either we are trying to find out these labels, or even if we can't deduce that it's a yes or no, we are trying to find out patterns in this part of the data. So minus the labels, in this part of the data we are trying to find some patterns. So what can we do with this data? One thing we can do is we can explore the data. So I took just the first 2 columns, the first 2 features, and I plot them. I took 2 because it's easier and you can visually see it in a 2D screen. So the sky and the temperature. So you have sky over here, sunny and rainy, and the temperature cold and warm. So if I plot these 4 values, sunny, warm, sunny, warm, sunny, warm, there are 3 sunny, warms. So we have those 3 over here, and there's 1 rainy and cold, which is over here. So just looking at this data, I can make a very good guess that there are 2 natural distinctions, 2 groupings, or 2 what we call as clusters, and this is a pattern. So we don't know whether this is a yes or a no, but we know that sunny and warm, there are 3 occurrences, so they form a cluster. We know that they are there, but we don't know what's the name. So we don't know whether it's a yes or no, whether it's something else, but we know that the groupings are there even without having the aid of these labels, as in the case of the supervised learning. So this is totally unsupervised. I did not use any training data. I just used the data here with no help from the labels. So what's the goal of clustering? If an artificial intelligent machine can automatically group the data into clusters, it can subsequently gain useful information from these clusters. So if once we can be able to find the clusters, then we can look at the data and say what is common between this data, because they tend to form, they have a similar behavior, they form a cluster, they form a group. So then we can go and manually deduce what is the meaning of that cluster. It could be the region, it could be the general model in which represents the cluster, it could be the number of clusters that are present, it could be the density of a cluster, or any other thing that we want. So what's the goal of clustering? A formal definition could be that the grouping of data into 2 or more groups such that data points in the same cluster are similar together in some way. So I have highlighted this in red, in some way, but dissimilar with data points in other clusters. So what we're saying is that if we have 2 clusters here, data points may be, this can be circles here. So these are similar in some way and different from, maybe we have triangles over here. We have triangles over here. So these are similar and these are similar, but if you look at them, they are dissimilar between themselves. So the clusters should have data points that are similar inside the cluster, but are dissimilar with data points in other clusters. So these circles are similar inside this cluster but dissimilar with these triangles. Now I said that these, I have noted it in red and in italic because we need to define what it means in some way. How do I know that these are similar? Visually, yes, I can see these are circles and these are triangles, but if I'm given a data which I cannot see, how do I figure out these are similar and these are not similar? For that we use the help of several different mathematical metrics. So for instance, this can be a Euclidean distance, which is nothing but the squared sum of their differences, and you take the under root. So this is the Euclidean distance. It's a distance measure, means that the closer 2 elements are, the smaller this distance will be. And the cosine similarity is just the dot product of the 2 vectors divided by their mod. So as I said, I will be using both the matrix notation and the vector notation. So this xi here is basically xi1 and xi2 and xip. It's a combination of all. This xi1, xi2, xip is the expanded form of this xi vector. So I can use the cosine. The cosine is not a distance, it's a similarity. It means that if two objects or two instances are similar, they will have a cosine value. If they are the same, they will have 1. If they are similar, they will have a value closer to 1. So the higher the better. In case of distance, if they are similar, they will have a value close to 0. If they are the same, they will have a distance of exactly 0. So the lower the better. And these are two examples. You can use any other metric, Jacquard, Kullback-Leibler distance, divergence, Manhattan distance, or any other. You can even make your own distance measure or similarity measure, what you want. But this is the definition of when we say that they have to be similar in some way. So similar in the way of either having a low distance or a high similarity value. So supervised learning or supervised algorithms are further classified into partitioning methods and hierarchical methods. Partitioning method means that you are considering all the data as one, and then you form different partitions of the data. In the hierarchical method, it's done in a very different way. In this lecture, we are going to look at the partitioning method, and in the next lecture, we are going to look at the hierarchical method. So let's look at the partitioning methods. And one of the most popular algorithms for the partitioning method is what is called as the k-means algorithm. So let's look at what k-means algorithm means. First of all, this k here is the number of clusters. So how many clusters do you want your clustering algorithm to form for you? Do you need 2 clusters? Do you need 3, 4, 5? You have to specify the clusters. K-means is not going to automatically find the clusters for you. You have to specify how many clusters you're looking for in the data. And the mean, so if you look at the name, it is k-means. So k is the number of clusters, and means means mean is the average. So it means that averages that are representing these k different clusters. So that's what this k-means refers to. Let's look at the algorithm. So we'll look at the algorithm before we take an example, and it's going to be pretty clear from the algorithm itself, because k-means is not a very difficult algorithm. It's a very straightforward and a very simple algorithm. But once we do the example, it's going to be even more clear. So let's look at the pseudocode for the k-means partitioning method. It says that in the input you need k. As I said, k is the number of clusters, and you need the data points containing n objects. So let's look at this data. So here we have all these data points. These are the n objects that we have. All these red dots or red circles, they are the objects, so you can count them and there will be n. We are looking for 3 clusters. You can see one shown by the dotted line, second one and third one. So here we have k equal to, so in this case our k is equal to 3, and if I count it, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21. So my n here is 21. I hope I counted it correctly. And the output is the k clusters that we want. So initially this dotted line won't be there. We have to find those dotted lines here. So this the output, that will be the clusters that we have found, and those clusters that we have found are going to be such that they minimize the squared error. And for this I'm particularly referring to the Euclidean distance measure over here. So I'm referring to this, I'm using this Euclidean distance. That's why I'm saying that I'm going to minimize the squared error. So how does it work? The first thing you need to do is arbitrarily means randomly, choose k objects as initial cluster centers. So in this data I'm going to choose, since my k is 3, I'm going to choose 3 different data points, and I will say these 3 data points are the centers of the 3 clusters that I'm looking for, and they're totally randomly chosen. To make it easy, what we have done is that we have Let us erase this. Yes, go back to the pen. So we have chosen these clusters. So this is the first one that we have. Let me call it C1, the center of cluster number 1. This is the second one. Let me call it C2, and this is the third one. Let me call this C3. So C is for the cluster. So initially I have only chosen, forget about all the rest of these points, and forget about this dotted black line at this moment. In the given data I have chosen 3. So arbitrarily choose k objects. K is 3. I have chosen 3, 1, 2 and 3. This is what this line is telling me to do. Then I am going to assign, so let's move on and go here and assign each object to the cluster to which the object is most similar based on the mean value of the objects in the cluster. So I have chosen 3, C1, C2, C3. There are 18 to all other data points left. So if I want to classify this data point, I am going to calculate the distance, so Euclidean distance or cosine similarity. I am going to find this distance over here, and then this distance, and then this distance. So I am going to find these 3 different distances, and naturally this looks close. So I will label this as part of C1 as well, and same goes for this and this. And once I have labeled all those as C1, so I have formed this dotted line that I have. So this is my first cluster. Similarly, when I am calculating for this point, I am going to calculate this distance, and this distance, and this one is shorter, so this belongs to the second cluster. Similarly, this belongs to the second cluster, and so on. And that's how I arrived at this cluster. Sorry, this is the third cluster, not the second one. And similarly we arrive at this. So once I have chosen arbitrarily the k objects, so this is C1, C2, C3, then for all the other objects I calculate their distance with these 3 centers. These C1, C2 and C3 are the centers of my clusters. So once I have done that, I am going to, so I'm finished with the first part, I am finished with this part, and now I move on, update the cluster means. So initially this was chosen to be my cluster center. However, now that I know that all these values are also part of my cluster, I am going to calculate a new mean based on all these values, and that mean is this one. So that's the new mean that I have. Similarly for this cluster, this is the new mean, and for this cluster, this is the new mean. It's in this side because we have these two as well as the new clusters. So once I am done with this, now this is no longer my C1, this has become my C1, this has become my C2, and this has become my C3, and then I'm going to repeat that until there is no change. It means that once I have C1, C2 and C3, again I am going to look at this, calculate the distance from here to here and this, and then probably assign it again to this cluster. But for this one I'm going to calculate this distance, and this distance, and perhaps now I'm going to classify. So initially this was belonging to the first cluster. With my new cluster centers, this now belongs to the third cluster. So you can see this dotted line over here. So it means that the values have changed, and similarly these two values now are closer to this point rather than this point. So at the end I end up with these 3 clusters, and this is going to be repeated. Maybe I can even change until I arrive, so I can put a dot dot. So this is a repeating process until I arrive at this, such that no new data point is changing. So everything now here is closer to this, and so this point is going to be closer to this one. This is going to be always be closer to this one. If you recalculate the center, it's going to be this again, and then all these data points will belong to this C1, and this is my C2, and this is my C3. However, now I have reached a stability such that successive iterations are not going to change C1, C2 and C3, and because these C1s are not changing, the distances won't change and the data points will remain in the same cluster. So this is my stopping criteria. My stopping criteria is when the centers do not change any longer. If they don't change, then the distances won't change and the labels for each of the data point won't change. So this is the pseudocode of the k-means algorithm. You can see it's very simple. To repeat, the first thing you need to do is, if k is 3, you choose 3 initial centers, and then for all the other data points you take the Euclidean distance with these 3 and you assign them to the cluster that has the least distance. Once you have assigned them, now the first cluster, instead of having 1 point, it has many points, and you use all those points, calculate the mean, and that mean will become C1, and then the same goes for C2 and C3, and then continue repeating that until there is no change and you are left with stable clusters, and this will be your final answer. So this is the output. This is the output. The output is k clusters, and these k clusters are such that they are going to minimize the sum of squared errors, and we can be sure because we use the Euclidean distance for that. So let's move on to the example and see how this works. So for this example, I have chosen 8 data points, and to keep it simple, we are going to have just 2 values, so x and y coordinates, so that we can easily draw it on a graph as well. So there are 8 data points, each with 2 coordinates, so x and y, and so this is my data points. The first thing I need to do is, if I have these data, the first thing I need to do is choose my initial cluster centers. So in this case it says 3, so my k equal to 3. It means I need to choose 3 points. So I need to choose 3 points, and those points have to be from within this data. So in this case I have chosen A1, A4 and A7. It could have been any other values because they are totally chosen at random. So this is my initial cluster. So I'm going to assume that my first cluster at this point have only one data point in it, and that data point is A1. So this belongs to C1, cluster number 1. This belongs to cluster number 2. This belongs to cluster number 3, and all the other data points are now unlabeled. It means they do not have a cluster at this point. We have to assign it. So for the rest of this example, instead of using the complicated Euclidean, I have to use a calculator to find out all the square roots. What I've done is I have replaced it with a simpler distance measure, which is the Manhattan distance. So if I have 2 data points, I'm just going to write, I'm just going to take the differences between them, the absolute differences. So when I'm taking an absolute, even if this is smaller and this results in a negative value, I'm going to ignore the negative values. I'm going to take the absolute distances, which will make the calculations a lot more easier. So what I need to do is my 3 data points that I've chosen as my cluster centers, I have represented them here. So this is the first cluster center. So this is my C1, my C2 and my C3. Now I need to do for all the rest of the data points. There are 8 in total. I have chosen 3, so there are 5 remaining. They are shown in blue here. For all of them, I have to calculate the distance between them and each of the 3 clusters. Note that when I have to cluster, I am representing here all the data points here. So all the 8 data points, including those that I had chosen as the cluster centers, they are also included in this data. So what I need to do is I need to fill this table. To see how I'm going to fill this table, let's look at the detail. Let me take this first data point, A1, which is 210, and then calculate the distance between this and C1, C2 and C3 respectively. This is shown in this table. So I have taken the first data points, which is A1, 210. If I calculate the distance between this and this, it's obvious this is also 210. It's the same data point. The distance is going to be 0, but let's just calculate it anyway. So this is going to be 2 minus 2 and plus we have 10 minus 10. So this is going to be 0 plus 0, which is 0, and that was obvious because it's the same data point. But let's look at the second data point. So I'm trying to calculate the distance between 210 and 58. So in this case, what I'm going to have is 5 minus 2. So the mod plus what I have is 8 minus 10. And again, I'm going to take the modulus. So this is 3 and this is minus 2. If you take the mod, this is 2. So I have 5. And if I move over to this center, I have 1 minus 2. Take the modulus plus 2 minus 10. Again, I take the modulus. So this is 1 plus 8, which is 9. So the three values, so the first data point A1, when I'm comparing it to the three centers C1, C2 and C3, I have the values 0, 5 and 9. So let's remember these values, 0, 5 and 9, and we're going to put it. So the distance between this is 0, 5 and 9. Now the next thing I need to do is, in the third step, is I have to choose now I have to label this A1. So I have to choose the smallest value. Naturally, this is the smallest value. It belongs to C1. So since this belongs to C1, I am saying that A1 belongs to cluster number 1. And in the same manner, I have to fill these and then assign a cluster here, and then fill these and then a new cluster, and so on. So when I repeat it for all other values, I calculate the distances with each of the three clusters, I end up with something like this. So 0, 5, 9, 0 is the smallest value, I put a 1, 5, 6 and 4, 4 is the smallest value, belongs to the cluster number 3, so I put a 3 over here, and so on. Now I see that my first cluster C1 has the element, it contains the element A1, and my second cluster C2, it contains the elements A3, A4, A5, A6, not A7, and A8. So 1, 2, 3, 4, 5, and then my C3 contains only 2 elements, which are A2 and A7. So at the end of my first iteration, I am left with 3 clusters, which are A1 belongs to the first cluster, A3, A4, A5, A6 and A8 belonging to the second cluster, A2 and A7 belonging to the third clusters, which are shown here. Now the final step I need to do is calculate the new mean for this before I go on to the next iteration. So to calculate the new means, this is very simple. There's only one data point, so the mean is going to remain the same. I have nothing to do, nothing to change here. For this, these are all the x's and these are all the y's. So to calculate the new mean, this is going to be 8 plus 5 plus 7 plus 6 plus 4. I'm adding these values and then divided by their 5 elements, because it's the mean, so divided by 5. And then for the y, I have a 4 plus 8 plus 5 plus 4 plus 9, again divided by 5. So this is 8 plus 5 is 13 plus 7 is 20, 26 and 30. So 30 divided by 6 is 30 divided by 5 is 6, and then 4 plus 8 12, and then 17, 21, and this is again 30, and this is going to be 6. So this is my new C1, this is my new C2, and here I have 2 plus 1 divided by 2 and 5 plus 2 divided by 2. So this is going to be 1.5 and 3.5. So this is my new C3. So 2, 10, 6, 6, 1.5, 3.5. I'm going to replace it. I'm going to cancel the old ones. So 2, 10, 5, 8 and 1, 2 are gone. The new ones 2, 10, 6, 6 and 1.5, 3.5 are in. And then I have to again calculate the distance between this and this, and then this and this, and this and this. And once I'm done, again, obviously this is going to be 0. So this is going to remain to cluster number 1, and I have to fill with all the other values. And I'm going to keep repeating that until the successive iterations do not change. So once I fill this, these are also all going to have values over here, and then once I have values, I'm at this stage. I'm going to calculate the new clusters, I'm going to calculate the new cluster centers, and I'm going to repeat this process, and I'm going to continue that until 2 successive iterations where these mean values do not change. That is my stopping criteria for the k-means. So this is, we can see that visually. So initially my A1, my A4 and my A7, these were the initial cluster centers, and then I used the Manhattan distance, and I calculated the distances between each of them, and I ended up with these 3 clusters. And with these 3 clusters I made new cluster centers. So this cluster centers remained here, we have a new cluster center here, and we have a new cluster center here. It's important to note that this is my new I think this was C3 and this was C2. So the cluster center does not necessarily have to correspond to a data point. It can be an arbitrary value calculated based on the means. So it doesn't have to be an actual data point. So that was the k-means. It's very easy to implement, it's very easy to run, and it's very fast because there's nothing complicated there. However, there's a problem with the k-means, and the problem is that when I run this, so since I chose A1, A4, A7, and I said that these were chosen randomly at the very beginning, if I choose maybe A1, A8 and A2, I'm going to end up with maybe a totally new result. If I chose A3, A5 and A6, so if these were the 3 initial clusters, I would be in a very totally different cluster set. So what this means is that if you run the k-means algorithm one time, you are going to get one result. You run it again, you are going to get another result, and you run it again, there's a possibility you get a third result, and the fourth and the fifth, and so on. So this is not a very deterministic algorithm. It means that from one run to another, you can end up getting different results. And the second thing is that the result that you're going to get, it will be very dependent on the initial cluster that you have chosen. So how accurate the result is will depend on how good the initial clusters points were. So there have been many improvements to the k-means. The first one is simple. It says that instead of using the means, because the mean use an arbitrary value, why not use the median? So for a new cluster, don't take the mean, just sort them and take the median value. And then there have been other improvements which says that maybe the initial points, instead of randomly, they should be chosen using some heuristic. And using this heuristic, I want to also share some experience, because I wrote a research paper on this with one of my students last year. So Haris was one of my students. He did his master's from here, and we wrote this paper which got published. And so it says a k-means based co-clustering algorithm for sparse and high dimensional data. So we use this instead of using random selection, we use a heuristic to select that. Now I'm just going to briefly explain what I did. It's not part of the exam. I'm not going to ask you to run this algorithm, but you should know that how changing the cluster centers or the way the clusters are being initialized can have a huge impact on the results. So what I did is that, for instance, in the k-means, there's a possibility I could have chosen this, and this. So this is C1, this is C2, and this is C3. That's one possibility. Obviously, it's not a very good possibility because these are not clusters. They should be part of the same clusters, not a different cluster. Maybe if you look at it, maybe this is one cluster, and this is a second cluster, and then this can be a third cluster, or if you can divide it, maybe there can be a fourth cluster here as well. But if you want three clusters, these are the three clusters that you are probably going to get. If I chose C1, C2, C3, it means everything is belonging to this. It means I can never arrive at these clusters. So what I did instead was that I'm going to choose only, so let's look at it. Select the first point randomly. So I'm going to select the first point at random. Let's say I choose this point. This is the first point I chose at random. Now if we're using k-means, I could have chosen this one as the second point, this one, any of them. But in our case, we said select the second point which is farthest from the first point. So the second point, this is farthest from the first point. So I'm going to calculate the distance, the Euclidean distance or the Manhattan distance between all pair of points. Sorry, not all pair of points, but this point and all the other points. And then this is the farthest point. So this is the second cluster I have chosen, C2. And then select the third point which is farthest from the first 2 points. So the third point is this one, which is collectively farthest from C1 and C2. So that was the first difference. You're not choosing randomly, but we are using some heuristic to choose this. The second part of the initialization for the k-means algorithm was that we said that instead of using only one, maybe if I choose just one center for each of these. So if this is the mean, so this is C3 and this is C1 and this is C2. Instead of choosing, sorry, this is C2. I'm going to keep the same notation. So this is C2 and this is C3. So instead of using just one mean, why not represent it with multiple centers? So in total I'm going to choose 5 centers. L is the number of data points that I choose to represent a cluster instead of a single mean. So for the second set of values that I have to choose, I'm going to choose for the second point in the first cluster, select a point that is closest to mu1. So this is the mean for the first center, and from the farthest from u2 to uk. So I'm going to select the second one which is closest to this one but farthest from this and this. So that's how I choose this C12, and then similarly I chose this one because it's closest to this, and then it's farthest from this one, and then we choose the C32, and because there are 5 we are going to iteratively. So at the end these 5 points are representing this cluster instead of just one simple centroid, and similarly these 5 points are representing this cluster instead of a simple centroid. So the two changes were the way the centroids are selected and the fact that a cluster is not represented by one mean but by multiple values. And then there was a third difference as well related to how the distance is calculated. We're not using cosine or Euclidean. We proposed our own distance measure. So the net result of all this was, here's the result we have. So M5, M10, M5, M2, M5, M10, Quora, Cornell and Washington, these are 6 different data sets They represent different data. You can find it on the internet. But the interesting point is, if we look at the result, this is the k-means result. So for the M2 data set, we had on average an accuracy of 0.76. So this 0.76 actually means 76%, because we are using the scale of between 0 and 1. So this is actually 76% accuracy, and a standard deviation of 12. So it means that if you run this k-means maybe 10 times on the M2 data set, each time you are going to have a different accuracy, and if you take the average of those 10 accuracies, you are going to end up with 76 with a standard deviation of 12. It means sometime it's going to be maybe 82, 83, and sometime it's going to be 65 as well. So this is the result. On the other hand, if you are using KCC, your accuracy has increased from 76%, it has increased to 92%, and the variation has decreased from 0.12 standard deviation to 0.02. It means not only that the algorithm has improved a lot, it is a lot more robust now. So a new run is going to give you a value which is very close to 92%. There is not a lot of variation between different runs of this algorithm. So you can see that by changing the values or changing the parameters, we can improve on the results. So the basic point is that, and the same goes for the other algorithms we saw. The decision tree, we are using entropy. The naive Bayesian, we are using probabilities. These are algorithms in themselves, and the k-means also. They are algorithms in themselves, but they are also a framework. So the KCC algorithm that we developed here, it was based on the k-means framework. It means that there's initially choosing of cluster centers, and then there is the iteratively assigning labels to different data points, recalculating the center, and doing it again and again. Except that the way the k-means chose its initial centers, we changed that. It chose one center, we are choosing many, and the distance measure the k-means is using, we have changed that. The framework is the same, but the specifics have been changed, and by doing that, we have massively improved the accuracy. And the reason I'm telling you that this is that when you're going to be applying some of these algorithms in the real world, there's no guarantee that if you are given, for instance, I can tell you from experience that if you are using a textual data, if you use k-means and you couple it with Euclidean distance, you are guaranteed to get pretty bad results. Cosine is a much better distance measure to use if you are using text data as compared to the Euclidean distance. So suppose you were using the text data and somebody asked you, go and try to cluster it. You go and you use an implementation of k-means, or it's so simple you can code it yourself, and you try it and you don't get good result. It does not necessarily mean that k-means is bad for this data. It means that you should also try some variations, or you need to develop your own variation which is very specific to your problem, the way we did, and we increased the accuracy from 76% to 92%, and in the case of the M5 data up to 95%. So we have increased the accuracy, even though if we have looked at the k-means, the initial results were not very promising. So you can do that. And this paper here, this is the reference of the paper. If you want, you can look at this paper. So Hussain and Haris, it was published in Expert System with Applications in 2019, and this is a journal which is one of the highly, in fact, currently according to Google Scholar, it's the #1 rated journal in the field of artificial intelligence. So it's a very good publication. You can go and read it if you want. It's not going to be part of your course, but for those of you who will be needing this for your practical work, for your jobs, there's a good approach you can use. So finally, to summarize, what we have done is, in the case of k-means, the centers, the first thing we have seen is that when you're using k-means, the centers don't have to correspond to actual data. They can be an arbitrary data because we are just computing the mean, the averages. So averages doesn't have to be real actual data points. The second thing we saw is that the algorithm is going to keep iteratively running until we find stable clusters. The third thing we see is that multiple runs of k-means may not result in the same values. So it means that it is non-deterministic in nature. And the accuracy of k-means does indeed depend on the initial selection of k-means, and that's why we have different results for different k-means, because we're not changing the Euclidean distance, but we are changing the initial centers, and therefore the initial center, choosing the good initial center is very important to getting good results. And finally, using smarter heuristics, for instance, I just showed you one with the same general framework, can greatly enhance your accuracy and your stability. So if you're ever going to encounter any one of these algorithms, don't just say this doesn't work. Try to figure out why it doesn't work. Can I change a few things? Maybe it's going to start working. So there are general frameworks. They have been used for quite a long time, and the reason they have survived so long, because computer science is changing very fast. So the reason these frameworks have survived very long is that they're pretty sound frameworks, and if you choose to change or upgrade or modify some of the metrics there you are using, you can still use them and get very good results. So that is it for today. If you have any questions, you can ask me either on MS Teams, you can email it to me, or you can post it in the YouTube comments, or finally you can ask me during the question answer session that we have at the end of the week. So I hope this was clear enough, and in the next lecture or in the next video we will be looking at this was the partitioning algorithm, and we are going to look at the hierarchical algorithm. So that's it for this video. Thank you for watching.